the universe explodes in supernovae. That is what we have always believed, the ultimate cosmic violence, the final death of a star that outshines entire galaxies. But we got it wrong. For decades, astronomers detected explosions 100 times more powerful than any supernova ever recorded. And we ignored them. We dismissed them. We called them statistical errors. The math screamed. The data defied every model. And now, evidence is emerging that changes everything we thought we knew about stellar death. Before you understand how stars die, you need to understand hypernovae. Before you grasp the cosmos, you need to know about the explosions that created the very atoms in your body. If you want to discover the science behind these cosmic monsters, hit that like button and subscribe right now. Brace yourselves. The revelation begins. Here is what we missed. In 1999, astronomers pointing their telescopes at a distant galaxy called SN 1998 BDW witnessed something impossible, an explosion that refused to follow the rules. The brightness kept climbing, and climbing and climbing. Every model of stellar physics predicted that a supernova reaches maximum luminosity and then fades. Predictable, understood, catalogued. But this explosion defied the script. It was brighter than expected, far brighter. The energy released was staggering. Scientists looked at the data again, then again. They checked their instruments. Had the sensors malfunctioned? Had cosmic radiation contaminated their observations? No, the data was clean. The phenomenon was real. They had discovered something the universe had been hiding from us for billions of years. This is the critical moment. This is when science changes, when the comfortable narrative breaks, when the universe reveals that it is far more violent than we ever imagined. A hypernova is not merely a brighter supernova. Think of it like the difference between a house fire and a nuclear explosion. Both are violent, both are destructive. But the scale, the mechanism, the energy release, everything is different. A hypernova releases energy equivalent to 10 to the 45th power joules. To put this in perspective, all the nuclear weapons detonated during the entire Cold War, every single bomb, every test, every arsenal from every nation combined, released less energy than a single hypernova in one moment, in one cosmic instant. One hypernova annihilates more through pure violent force than humanity's entire destructive capacity. The light itself travels differently from a hypernova. When matter is ejected from this explosion, it moves at 99% the speed of light. This is not debris drifting lazily through space. This is apocalyptic ejecta. Stellar material moving so fast that relativistic effects become crucial. The radiation pressure is so intense that it tears atoms into subatomic particles. The magnetic fields reach impossible strengths, stronger than anything we can create in laboratories on Earth. Thousands of times stronger. The temperature at the core of the explosion reaches billions of degrees. The density climbs toward the neutron star regime. This is not just science. This is extreme science. This is the universe operating at the edge of what physics allows. But here is where the mystery deepened. Hypernovae were not isolated incidents. They were not one-time anomalies. As telescopes improved, as detectors became more sensitive, astronomers began finding them everywhere, in distant galaxies, in the ancient universe, in the local cosmic neighborhood. The James Webb Space Telescope recently confirmed that hypernovae were common in the early universe, more common than anyone expected. The early cosmos was not peaceful. It was not a gentle realm of slowly evolving stars. It was a war zone, a battleground where massive stars lived fast, burned bright, and died spectacularly. Every few seconds, somewhere in the observable universe, a hypernova detonated. Unimaginable violence distributed across the cosmos like cosmic machine gun fire. Scientists began asking the crucial question: what creates a hypernova? What stellar conditions are necessary? What mechanism allows an explosion so violent that it defies the normal rules of stellar death? The answer emerged from deep theoretical work and careful observations. Hypernovae require specific conditions. A star must be extraordinarily massive, at least 50 times the mass of our Sun. The star must be rotating at extreme speeds, near the theoretical limit where the centrifugal force almost overcomes gravity. The star must possess incredibly strong magnetic fields. The iron core must reach a critical density where it can no longer support itself. All these conditions must align, and when they do, when all the pieces are in place, the universe creates something catastrophic. The ejected material from a hypernova becomes a beacon, a lighthouse signal visible across billions of light years. Some hypernovae produce gamma-ray bursts, the most energetic electromagnetic radiation known to physics. These jets of radiation are so intense that they pierce through the cosmic dust that normally obscures distant observations. They are like cosmic spotlights sweeping across the universe. When a hypernova detonates, it can be brighter than the entire galaxy containing it. Imagine a single explosion outshining billions of stars. Imagine the raw power required for that. This is not metaphor. This is observational fact. This is what happens at the edge of what the universe can do. For centuries, we thought we understood the cosmos. We thought we knew how stars lived and died. We had equations. We had models. We had textbooks filled with confident assertions. And then the universe revealed that we had been staring at only a fraction of the picture. We had been looking at stellar explosions like someone observing only the surface of an iceberg, while the true mass lurked beneath. Hypernovae are that hidden mass. They are the violent truth that changes everything. They are the cosmic monsters that force us to rewrite physics. But what they discovered next was even stranger. Imagine two explosions, both devastating, both cosmic, but one is 1,000 times more powerful than the other. That is the chasm separating supernovae from hypernovae. For most of modern astronomy, we knew only about supernovae. They were the ultimate violence in our understanding. A star dies. Its core collapses. Matter rebounds in a thermonuclear explosion. The fireball expands. Light floods across the cosmos. We built entire theories around this process. We understood it. We measured it. We could predict what would happen. Supernovae release energy on the order of 10 to the 44th power joules. Unimaginable power by human standards. But this is where the story takes a turn. This is where the universe reveals a tier of violence that supernovae cannot match. A hypernova is not simply a brighter supernova. This is crucial to understand. It is not just more of the same thing. It is categorically different. Think of it like comparing a car crash to an atomic bomb. Both are explosions. Both release energy violently. But the scale, the mechanism, the aftermath, everything is transformed. A supernova is a thermonuclear reaction in the outer layers of a star, or the explosive rebound of a collapsing core. The energy comes from nuclear fusion or gravitational potential energy. It is violent, but comprehensible within classical stellar physics. A hypernova is something else entirely. The energy reaches 10 to the 45th power joules or beyond. This is 100 times more powerful. The ejection velocities reach 99% of the speed of light. At a supernova, matter is ejected at 10 to 30% of light speed. The difference is staggering. At a hypernova, relativity becomes critical. Time dilation matters. Space is warped. The physics enters a regime where classical mechanics breaks down. The mechanisms are profoundly different. A standard supernova comes in two varieties. The first is a Type II supernova. A massive star's iron core collapses and rebounds catastrophically. The shockwave races outward through the star, ripping it apart. The star explodes. The light is brilliant. The expansion is violent, but it is comprehensible. We can write equations describing it. We can plug in numbers and predict outcomes. The second variety is a Type Ia supernova, a white dwarf pulling material from a companion star, accumulating mass until a thermonuclear explosion ignites across its surface. Both are well understood phenomena. Both fit into our models. Both behave mostly as predicted. A hypernova requires conditions that push physics toward its breaking point. You need a star so massive that its destiny is sealed from birth. A star at least 50 solar masses, possibly 100, possibly more. Such a star burns through its fuel in only a few million years. It lives fast. It dies hard. As the core collapses, it does not simply rebound. Instead, something remarkable happens. The rotation of the star becomes critical. If the star is spinning rapidly, and these cosmic monsters do spin, the angular momentum becomes extraordinary. The infalling material does not fall straight toward the center. Instead, it spirals inward. A disk forms, an accretion disk around a newly born black hole or neutron star. This disk channels energy. It focuses the explosion into two jets, beams of matter and radiation erupting from the star's poles at near light speeds. These jets are the difference between a supernova and a hypernova. The jets collide with the surrounding material. They heat it. They accelerate it. They amplify the explosion. The explosion breaks free. The star is torn to shreds. Not just disrupted, utterly annihilated. The outer layers are blown to smithereens. The material spreads into space at velocities that make supernovae look pedestrian. This is why hypernovae are so bright. This is why they can be seen from across the universe. The energy is concentrated. The beam is focused. The photons are streaming outward with such intensity that they create a lighthouse visible billions of light years away. Energy is the defining metric. A typical supernova releases 10 to the 44 power joules of kinetic energy, the energy in the moving debris. A hypernova releases 10 to the 45 power or more, 100 times more. But the impact is not merely 100 times greater. The effects are amplified across every parameter. The brightness is 100 times greater. The luminosity is staggering. The radiation pressure is brutal. The ejection velocities are superhuman. The debris from a hypernova travels through space at speeds where time literally moves differently than on Earth. Relativity becomes the language you use to describe the explosion. Not classical mechanics, not Newton's laws, Einstein's equations. This is the threshold where the universe reveals its extreme side. The aftermath diverges equally. After a supernova, we find a neutron star or a planetary nebula, organized remnants, observable structures. A hypernova leaves behind something more exotic, possibly a black hole, possibly a magnetar. a neutron star with a magnetic field so intense it would shred any material within thousands of kilometers. The surrounding space is flooded with high-energy radiation, gamma rays, X-rays, ultraviolet light. The shock waves propagate outward for decades, centuries, even millennia. They heat the surrounding interstellar medium. They create expanding shells of glowing gas visible as supernova remnants. But these remnants from hypernovae are different. They are brighter. They expand faster. They glow with more exotic radiation. They tell a story of extreme violence that exceeded all predictions. The discovery of this distinction rewrote astronomy. Before 1999, we thought we understood the spectrum of stellar explosions. We had our categories. We had our equations. We had confidence. Then SN 1998 BW arrived. Then GRB 030329. Then GRB 170205b. Then countless others. Hypernovae were revealed not as rare anomalies, but as a distinct class of events occurring throughout cosmic history. Some estimates suggest that in the early universe, hypernovae were more common than conventional supernovae. The universe was more violent then. The stars were more massive. The explosions were more extreme. We had been blind to this reality until our instruments became sensitive enough to see it. This changes how we interpret the cosmos. This changes how we understand stellar evolution. This changes how we think about the universe's capacity for violence and destruction. And it raises a profound question that demands an answer. But what forces could possibly create such extreme explosions? What stellar conditions could build an explosion 100 times more powerful than anything else we have ever observed? What cosmic mechanism could generate such catastrophic energy release? Physics has limits, or so we thought. For centuries, physicists built models of the universe, beautiful equations, elegant mathematics, laws that describe how everything works, gravity, electromagnetism, nuclear force. We tested them. We verified them. We built entire civilizations on the technology that emerged from understanding these laws. But then we encountered hypernovae, and the physics screamed. The equations pushed toward infinity. The models broke. The comfortable certainties shattered. Because hypernovae exist at a boundary that physics itself struggles to describe. They are places where multiple extreme forces converge simultaneously, where gravity and rotation and magnetism battle for dominance, where matter reaches densities that make human intuition collapse under its own weight. Start with gravity. Gravity is relentless. It pulls. It crushes. It never rests. At the core of a massive star, gravity has been pulling inward for millions of years. Every layer of the star presses down on the layers below. The pressure climbs, the temperature climbs, the density climbs. At the star's core, the pressure is so intense that hydrogen fuses into helium. Helium fuses into carbon and oxygen. Carbon fuses into heavier elements. The star builds element by element, layer by layer. Iron, nickel, silicon, an onion of increasing density, an onion of increasing temperature, an onion where the outermost layers are already hotter than the interior of most other stars. This is extreme, but it is not hypernova level extreme, not yet. But as the star ages, something inevitable happens. The fuel runs out. Iron cannot fuse into anything lighter. It would require energy rather than releasing energy. The core becomes a ball of iron, inert, dead, and gravity keeps pulling. It does not care that the fuel has exhausted. Gravity is patient. Gravity is absolute. Gravity keeps pulling inward. The pressure keeps climbing. The density keeps increasing. Iron nuclei are crushed together. Electrons are forced into protons. Neutrons are created. The core becomes a sea of neutrons. The density climbs toward a neutron star's density, so compact that a teaspoon would weigh 1 billion tons. Imagine that, 1 billion tons in a teaspoon. That is what gravity accomplishes. That is the crushing power of gravity when given enough mass and time. At this point, something has to give. The inward crush is so intense that pressure cannot hold it back anymore. The core collapses catastrophically. It implodes. The free fall is terrifying. Matter racing inward at speeds approaching the speed of light. Electrons being annihilated. Protons being crushed. The density climbing past neutron star density towards the threshold of a black hole. The infall is so rapid that it releases energy. Gravitational potential energy, unimaginably vast amounts of it, is converted into heat. The temperature reaches billions of degrees, trillions of degrees. The neutrinos streaming out carry tremendous energy, so much energy that they could heat the outer layers of the star and trigger the explosion outward. This is a supernova. This is the moment when the inward crush meets an outward explosion. The rebounding core drives a shock wave through the star. The shock wave races outward. It heats. It accelerates. It blasts stellar material into space at velocities of 30,000 kilometers per second, 30% of light speed. Violent, catastrophic. One of the most powerful events in the universe. But this is merely a supernova. This is not extreme enough for a hypernova. The universe has something more terrible in mind. Now introduce rotation. Take that same massive star. Assume it is spinning. Not slowly, rapidly. A massive star at the edge of instability. Spinning so fast that the centrifugal force almost overcomes gravity at the equator. The star is bulging at the equator from the spin. The material wants to fly apart, but gravity holds it barely in check. Angular momentum is building. Angular momentum that cannot go anywhere. As the star collapses, this angular momentum is conserved. Just as a figure skater spinning faster when pulling arms inward, the collapsing core spins faster and faster. The rotation rate climbs toward the theoretical limit, near the speed of light at the surface. At this rotation rate, relativity becomes critical. Space itself is dragged along by the spinning core. Gravitational frame dragging. Time moves differently in different locations. The core is not simply hot and dense. It is spinning so fast that the topology of space-time becomes relevant. Add magnetic fields. The star generates powerful magnetic fields through dynamo action in its turbulent core. These fields are not weak. They are powerful. Thousands of times more intense than Earth's magnetic field. As the core collapses, the magnetic field lines are frozen into the plasma. They cannot escape. As the core contracts, the field is compressed into a smaller volume. Just as pushing magnetic field into less space increases its strength, the collapsing core amplifies the magnetic field. The field strength climbs. It climbs higher. The field becomes so intense that it warps space-time. It generates tremendous pressure. Magnetic pressure fighting against gravity. Magnetic forces trying to tear the core apart while gravity tries to crush it smaller. Now all three forces meet. Gravity crushing inward. Rotation spinning the core into relativistic speeds. Magnetic fields amplifying and redirecting the explosion into focused jets. The system is not in equilibrium. It is not stable. The forces are in violent conflict. The math describing this situation becomes extraordinarily complex. Einstein's equations coupled with magnetohydrodynamics, relativity combined with nuclear physics, computer simulations crash from the numerical complexity. The physics enters a regime where even calculating the outcome requires the most powerful supercomputers humanity has built. The mathematics screams under the load. The equations struggle. The universe is doing something that taxes even Einstein's framework. And when these three forces reach their maximum conflict, when gravity has compressed the core beyond neutron star density, when rotation has reached the relativistic limit, when magnetic fields have been amplified to impossible strengths, the result is a hypernova. The explosion is not a gentle rebound. It is a catastrophic, violent release of all this accumulated tension. The core either collapses into a black hole or remains as an exotic magnetar. Either way, the explosion is unleashed. The jets are launched. The star is annihilated. The energy released is 100 times greater than a supernova. The matter is accelerated to 99% of light speed. The radiation pressure is so intense that it shreds atoms themselves. This is extreme physics. This is the universe operating at the boundary of what any theory can describe. This is where gravity and relativity and quantum mechanics all matter simultaneously, and scientists are still debating exactly how this process works, still arguing about the details, still refining the models, because hypernovae force us to confront the most extreme conditions possible without creating a black hole from which nothing can escape. But there is more. There is something even stranger about the stars that create these explosions. Most stars live quietly. Our sun has been burning steadily for 4.6 billion years. It will continue for another 5 billion more. A peaceful existence, a slow fade. The sun is not remarkable. It is not special. It is typical, average, ordinary. But most stars are ordinary. The universe is filled with red dwarfs, small, cool, long-lived stars that will shine for hundreds of billions of years. They are the true citizens of the cosmos. They are stability personified. They are time incarnate. But some stars are different. Some stars reject the ordinary. They burn bright and fast. They live lives of intensity measured in millions of years rather than billions. And when they die, they do not fade quietly. They explode catastrophically. These are the stars that create hypernovae. These are the cosmic monsters. A hypernova, progenitor star, the star destined to become a hypernova, begins its existence as something truly monstrous, at least 50 times the mass of our sun, possibly 100 times more massive, possibly even larger. Imagine a star so massive that if you placed it where our sun is, it would extend nearly 1/3 of the way to Earth. Its diameter would dwarf the orbit of Mercury. Its volume would be incomprehensibly vast. Its gravity would be devastating. Its power would be overwhelming. And yet, such stars exist. They exist throughout the universe. We have observed them. We have measured them. We have watched them burn through their fuel at rates that make ordinary stars look like embers. The surface of such a star is terrifying. The temperature reaches 100,000 degrees Kelvin. Compare this to our sun's mere 5,800 Kelvin surface temperature. The hypernova progenitor is 17 times hotter. The radiation flooding from its surface is ultraviolet and beyond. Lethal radiation that would strip electrons from atoms at a distance of light years. The luminosity is equally extreme. A hypernova progenitor shines millions of times brighter than our Sun. If you place such a star at the distance of Earth's Sun, it would incinerate our planet instantly. The radiation pressure would be sufficient to blow away planetary atmospheres. Nothing could exist within the star's sphere of influence. It is a stellar tyrant, a cosmic bully, a force of nature that reshapes everything around it. But the true marvel is the interior. Deep inside, the star is burning fuel at a rate that seems impossible. Hydrogen fuses into helium at ferocious rates. The core temperature reaches tens of millions of degrees. The pressure is crushing. The density is extreme. Fusion reactions are occurring at scales that dwarf all the nuclear weapons humanity has ever built. In the core of such a star, more energy is released per second than humanity has ever generated in its entire history. This star is not slowly burning. It is running a thermonuclear fire hose at maximum intensity, and the fuel is running out fast. This is the critical fact. These massive stars have very short lifespans. A star like our Sun has a main sequence lifetime of about 10 billion years. A hypernova progenitor, only a few million years. 3 million, 5 million, perhaps 10 million at most. These are cosmic mayflies. They are creatures of extreme intensity, living lives compressed into geological instants. A massive star is born, burns its fuel frantically, and dies before a blink of cosmic time has passed. And when the fuel runs out, the consequences are apocalyptic. The life cycle of a massive star is a descent into darkness. The star begins with a core of hydrogen fusing into helium. This phase lasts a few million years. The star is stable but extremely luminous. It is easily visible across light years. Then the hydrogen is consumed. The core contracts. The temperature climbs. Helium begins fusing into carbon and oxygen. The star expands into a red giant phase. This lasts longer, hundreds of thousands of years. The star becomes even more luminous. It is a red beacon in space, a warning sign that something extreme is happening. Then the helium burns out. The core contracts again. Carbon begins fusing into neon and magnesium. The star becomes unstable. It pulsates. It sheds mass. Winds of stellar material stream from its surface at velocities of thousands of kilometers per second. It is a dying giant thrashing in its final agony. But it is not dead yet. Element by element, the star builds heavier nuclei. Oxygen fuses, neon fuses, magnesium fuses, silicon fuses. Each fusion stage burns hotter and faster than the last. Each stage lasts shorter, years instead of millennia, days instead of years, hours instead of days. The star becomes unstable. It becomes chaotic. The outer layers are blown away by stellar winds. The core is exposed. The structure becomes increasingly exotic. The star becomes a Wolf-Rayet star, a stellar skeleton stripped to the bone. A furnace exposed to the cosmos, a star with no patience, only power. And finally, silicon begins fusing into iron. This is the threshold. This is the point of no return. Iron cannot fuse into anything heavier without energy input. The star cannot continue building nuclei. The fuel runs out, the core collapses, and a catastrophic chain reaction begins. The core implodes. The temperature climbs beyond anything achieved before. Neutrinos stream out carrying away energy. The core reaches densities beyond neutron stars. And then something terrible happens. The core rebounds. The infall halts. The material bounces back outward. A shockwave races through the star. And if the conditions are perfect, if the star is massive enough, if it is rotating fast enough, if the magnetic fields are strong enough, the shockwave does not stall. It does not fade. It accelerates. It breaks through the star's outer layers, and a hypernova is born. The star is annihilated. The entire structure is torn to shreds. Billions of tons of stellar material are ejected into space at near light speeds. Everything the star was, every layer built through billions of years of stellar construction, every shell of elements fused in the core, is scattered into the cosmos. These stars have no gentle deaths. These stars do not fade away. They do not settle into neutron stars or white dwarfs. They explode, catastrophically, completely, utterly. They transform into cosmic monsters. And yet, there is something even more critical about these stars. Something that determines whether they live or die. Something that determines whether they create a supernova or a hypernova. That something is rotation. A spinning star is a star with a destiny. Not all stars spin. Some rotate leisurely. Our sun completes one rotation every 25 days. Unhurried, peaceful. A gentle spin that barely matters to its physics. But massive stars are different. Massive stars are born spinning. They inherit angular momentum from the cosmic dust cloud that formed them. And as a star collapses and contracts during its life, that angular momentum is conserved. A collapsing star spins faster. Just as a figure skater pulling their arms inward spins faster, a contracting star must spin faster to conserve angular momentum. It is a law of physics, inviolable, absolute. And for the hypernova progenitors, this law becomes catastrophic. Imagine a star 100 times the mass of our sun. Imagine it spinning, not slowly, rapidly. The equator of the star is moving at tremendous speeds, tens of thousands of kilometers per second, perhaps even faster. The velocity climbs as the star evolves. The star contracts. The core gets smaller. The rotation rate climbs and climbs and climbs. The mathematical limit is the speed of light. A star cannot rotate faster than that without tearing itself apart. But these cosmic monsters approach that limit. They approach the theoretical edge of what physics allows. A star rotating at 90% of light speed at its equator is not rare among hypernova progenitors. 95% of light speed. Some approach even closer to that impossible threshold. At these rotation rates, something extraordinary happens. Gravity and centrifugal force enter into direct competition. At the poles of the star, gravity wins. The material is pulled inward. Gravity dominates, but at the equator, centrifugal force is powerful. The material wants to fly outward. Gravity barely holds it in place. The star develops an extreme bulge at its equator. It becomes oblate, flattened at the poles, swollen at the equator. The equator becomes so distended that it is nearly breaking free from the star's gravity. The star is on the verge of shedding its equatorial layers. It is teetering on the edge of instability. One more increase in rotation, one more collapse of the core, and the equilibrium breaks. Material tears away. The star begins to shed its outer envelope. This is critical to understanding hypernovae. Rotation creates instability. Rotation creates asymmetry. Rotation creates conditions where the star cannot remain stable as it collapses. A slowly rotating star collapses symmetrically. The core falls inward uniformly. The shockwave propagates outward uniformly. The explosion is spherical. This is a supernova. but a rapidly rotating star collapses asymmetrically. The poles collapse inward while the equator resists. The collapse is chaotic. The core develops inhomogeneities. The rotation amplifies these inhomogeneities. The collapse becomes non-uniform. And from this chaos, something emerges. Something focused. Something directed. An axis forms, a line of symmetry. And around this axis, a disk forms. This disk is the key to a hypernova. As the core collapses, material spirals inward around the rotation axis. The angular momentum must go somewhere. It cannot simply vanish. Instead, it drives the formation of an accretion disk, a structure similar to the disks around black holes, but born from the collapsing core of a dying star. This disk becomes incredibly hot, incredibly dense, incredibly energetic. Material is accelerated to near light speeds as it spirals inward. Magnetic field lines are compressed and amplified by the infalling material. The disk becomes a machine, an engine converting gravitational potential energy into directed motion. And from the poles of this disk, jets emerge, beams of material and energy launching outward along the rotation axis. These jets are not gentle, they are violent. They move at 99% of light speed. They are composed of relativistic plasma, matter stripped of electrons, moving so fast that relativistic effects are critical. The jets bore outward through the star's outer layers. They collide with the surrounding material. They heat it. They accelerate it. They amplify the explosion. The jets break through the star's surface. They emerge as the hypernova's characteristic features, the narrow beams of radiation that can be observed across billions of light years. Rotation also determines the efficiency of the explosion. A supernova from a non-rotating massive star releases its energy somewhat uniformly in all directions. Wasteful, inefficient. Much of the energy goes into heat and radiation that dissipates into space. But a hypernova focuses its energy. The jets concentrate the explosion. The energy is funneled into two directions. This focusing makes the explosion more brilliant, more energetic, more capable of breaking through dust and gas that would obscure a supernova. This is why hypernovae can be seen from the other side of the universe. This is why they are cosmic lighthouses. This is why they outshine entire galaxies. Rotation makes them more efficient. Rotation makes them more powerful. The rotation rate determines which of several hypernova types will occur. Below a certain threshold, the hypernova is weak. Above the threshold, a standard hypernova emerges. At even higher rotation rates, the hypernova becomes exotic. The jets become more focused. The energies climb higher. The brightest hypernovae, the superluminous supernovae, occur when rotation rates approach their theoretical maximum, when the star is spinning at the absolute edge of stability, when the centrifugal force is nearly equal to gravity, when the laws of physics are straining to remain intact. But rotation alone cannot explain hypernovae. Rotation creates the geometry. Rotation creates the jet structure. But what amplifies the jets? What channels the energy? What takes the collapse and transforms it into the most powerful explosion in the universe? The answer lies in something even more extreme. Something that surpasses rotation in its intensity. Something that bends space-time itself. It is magnetism. Magnetism is invisible. We cannot see it. We cannot touch it. But we can feel its effects. A magnet pulls metal towards itself. Invisible force acting across empty space. Magnetism shapes our planet. It protects us from the solar wind. It guides migratory birds across continents. It powers the engines of modern technology, but terrestrial magnetism is weak. Earth's magnetic field would barely deflect a compass needle if the needle were made of neutron star material. It is feeble, insignificant, but in the cores of dying massive stars, magnetism becomes something else entirely. Magnetism becomes a force that rivals gravity. Magnetism becomes a power that shapes stellar explosions. Magnetism becomes impossible. The magnetic field strength is measured in units called Tesla. A refrigerator magnet produces a field of about 0.001 Tesla. Weak, barely noticeable. Earth's magnetic field at the surface is about 0.00005 Tesla. Tiny, negligible from any physics perspective. Even the strongest magnets humans can create in laboratories, pulsed magnets used in research, reach about 100 Tesla. Impressive by human standards, powerful enough to levitate objects, powerful enough to generate forces that are palpable. But this is still trivial compared to the cosmos. A neutron star's magnetic field reaches 10 to the 8th power Tesla, 100 million Tesla. The magnetic field of a magnetar, an exotic form of neutron star, reaches 10 to the 15th power Tesla or beyond. Quadrillions of Tesla, numbers so large they cease to have human meaning. Now consider the core of a hypernova progenitor. As the star collapses, its magnetic field is compressed. The field lines are frozen into the plasma. They cannot escape. As the volume shrinks, the field strength climbs. A star with an initial magnetic field of 1 million Tesla compressed into a space 1,000th. The original volume will see its magnetic field amplified 1 billion times. The math is relentless. Compression amplifies magnetism. And in the chaotic collapse of a hypernova progenitor, compression reaches extreme levels. The core density climbs past normal stellar densities, past white dwarf densities, past neutron star densities. The magnetic field is crushed into progressively smaller volumes. The field strength climbs past 1 billion Tesla, past 1 trillion Tesla. The field enters a regime where it is as strong or stronger than the magnetic fields of magnetars. The field becomes dominant. The field becomes catastrophic. At these field strengths, magnetism stops being a minor player. Magnetism becomes a force equal to gravity itself. Magnetic pressure builds. Magnetic pressure pushes outward. It fights against the gravitational crush. The two forces collide. Gravity wants to compress the core. Magnetism wants to blow it apart. The battlefield is the stellar core. The stakes are the fate of the star. And when these two titanic forces collide, the result is not equilibrium. The result is chaos. The result is instability. The magnetic field does not remain smooth and uniform. Instead, it develops structure. The field lines twist. They tangle. They create vortices. The field becomes turbulent. A magnetic hurricane. A magnetic tornado. A magnetic tempest of unimaginable ferocity. The magnetic field begins to channel the infalling material. Remember the accretion disk that forms from the star's rotation? The magnetic field is threading through this disk. The field lines wrap around the disk like cosmic barbed wire. As material spirals inward along these field lines, the motion generates electric currents. Enormous currents. Currents so large that they would dwarf any electrical current ever produced on Earth. These currents generate additional magnetic fields. a feedback loop, a dynamo. The accretion disk becomes a machine for amplifying magnetism. The machine keeps running. The field keeps growing. The currents keep increasing. The system becomes increasingly turbulent, increasingly chaotic, increasingly extreme. And then the jets emerge. The magnetic field channels material from the disk into bipolar jets. The jets are not random. They are not chaotic. They are structured by magnetism. The field lines guide the jets along the star's rotation axis. The jets follow magnetic highway. The material is confined, focused, directed. The magnetic field prevents the jets from spreading outward. The jets stay narrow. The jets stay powerful. A magnetic nozzle. A stellar engine. The magnetic field is doing the work of creating, focusing, and accelerating the most energetic jets in the universe. Without the magnetic field, the jets would be diffuse. Without the magnetic field, the explosion would be weaker. The magnetic field makes hypernovae hypernovae. The magnetic field amplifies the explosion 100-fold. The specific energy of hypernovae jets, the energy per unit mass, is enormous precisely because magnetism is doing this focusing work. A hypernova jet may have lower total mass than a supernova ejection, but the mass is moving faster. Much faster. The magnetic field is preventing the material from spreading. Instead of dispersing across a wide angle, all the energy is concentrated into a narrow beam. The temperature climbs, the density climbs, the velocity climbs. Everything climbs because magnetism is squeezing the system. The same total gravitational energy is being released, but it is being funneled into a smaller volume, accelerated to higher velocities, and compressed into narrower beams. The magnetic field also amplifies the radiation. As charged particles move through intense magnetic fields, they radiate electromagnetic energy. This is synchrotron radiation. The radiation is intense. The radiation is penetrating. The radiation is responsible for much of the hypernova's brightness in the early phases. The magnetic field is converting kinetic energy into radiation. The magnetic field is making hypernovae glow. The magnetic field is making hypernovae visible. Without magnetism, hypernovae would be invisible, undetectable from Earth, unknown to astronomy. But with magnetism, hypernovae are cosmic beacons. They shine so brightly that they can be seen from the opposite end of the observable universe. The magnetic field structure is complex. It is not a simple dipole like Earth's field. Instead, it develops multiple configurations: twisted field lines, helical structures, kink instabilities. The field becomes increasingly convoluted as the core collapses. The complexity increases. The energy stored in the magnetic field increases. The field becomes increasingly unstable, and eventually, the instability can no longer be contained. The field configuration becomes impossible to maintain. The field undergoes a dramatic reorganization, a magnetic reconnection event. The field lines snap. They reform. Explosive energy is released. This reconnection event may be the final trigger that launches the jets and initiates the full hypernova explosion. Magnetism is the hidden architect of hypernovae. Rotation provides the geometry. Gravity provides the energy. But magnetism is the force that orchestrates the explosion. Magnetism is the difference between a fizzle and a catastrophe. Magnetism is the reason hypernovae are 100 times more powerful than supernovae. And yet, the story becomes even more extreme when we consider the moment when magnetism and gravity reach their ultimate confrontation. When the core collapses past the point of no return, time stops. or so it seems. In the final moments before a hypernova, the core of the dying star reaches a critical point, the point of no return, the moment when physics as we understand it begins to break down. The iron core can no longer support itself against gravity. The pressure is insufficient. The temperature is no longer climbing. No more fusion reactions are occurring. The star has reached the end of the line. There is nowhere to go but inward. There is nowhere to go but collapse. And when collapse begins, it is unlike anything else in the universe. It is not a gentle settling. It is not a quiet fade. It is an implosion, a catastrophic inward rush of matter at speeds that defy comprehension. The core begins to fall. Matter is accelerated inward by gravity. Iron nuclei, electrons, subatomic particles, everything is falling toward the center. The infalling material accelerates, faster and faster. The infall velocity climbs toward escape velocity, then exceeds escape velocity. Material is falling so fast that nothing could escape, not even if it were propelled outward at the speed of light. The infalling material reaches speeds of 100,000 kilometers per second, 1/3 of light speed, then faster. The material is compressed, squeezed into smaller volumes. The density climbs. What was already a stellar core, already one of the most extreme environments in the universe, becomes even more extreme. The density climbs past neutron star density, past the density of atomic nuclei, toward densities that have never been observed, never been measured, never been adequately described by any theory. The pressure climbs. Gravity is crushing. Inertia is resisting. The two forces collide. The pressure builds. The temperature builds. Electrons are forced into protons. Neutrons are created. The core becomes a sea of neutrons. But the pressure keeps climbing. The collapse does not stop. Neutrons begin to merge. Strange matter forms. The core enters a regime of physics that is purely theoretical. Nobody has ever observed these densities. Nobody has ever created these conditions in a laboratory. But physics demands that such conditions can exist. And in the core of a hypernova progenitor, those conditions are reached. The collapse happens in milliseconds, in tenths of a second, in moments so brief that they are almost instantaneous from a human perspective. But from the perspective of physics, it is a drama, a narrative with distinct acts. The core collapses homologously. The density profile remains similar as the core contracts uniformly. This phase lasts until the density reaches nuclear density. Then the collapse stalls. Nuclear forces become relevant. The incompressibility of nuclear matter becomes important. The collapse slows, briefly, for an instant. The infalling material reaches a maximum compression, and then the shock. The infalling material cannot fall any further. It hits the incompressibility of matter itself. The rebounding shock races outward. Material that was falling inward suddenly encounters a wall of resistance. The material bounces. The momentum is reversed. An outward shockwave is born. A shockwave propagating from the center of the core toward the surface. This shockwave is traveling through material at tremendous density. It is traveling through material where temperatures exceed 10 billion Kelvin. The shockwave heats the material. The shockwave accelerates it. The shockwave begins the process of blowing the star apart. But here is where the story takes a critical turn. The shockwave is losing energy. As it propagates outward through the star, it encounters denser material that has been compressed by the weight of all the layers above it. The shockwave is doing work. It is lifting material. It is accelerating material. It is pushing against gravity, and gravity is winning. The shockwave is losing energy. It is slowing down. By the time the shockwave reaches the outer layers of the core, it has lost so much energy that it is beginning to stall. The shockwave is struggling to break through. The shockwave might not make it. The shockwave might reverse direction and fall back inward. And if that happens, the star does not explode. The supernova fails. The shockwave stalls. The material falls back inward toward the newly formed neutron star or black hole. And the star does not become a beautiful explosion lighting the cosmos. The star collapses entirely into darkness. This is the crisis moment. This is the moment that separates a stellar explosion from a stellar implosion. Some massive stars might collapse into black holes directly without ever exploding. Some massive stars might fail to explode because their shock waves lose too much energy. These are the cosmic disasters, stars that die without a final brilliant display. But some stars have salvation. Some stars have a mechanism that prevents complete collapse. Some stars have jets. The magnetic jets from the core travel at nearly light speed. They are composed of relativistic plasma. They are incredibly narrow. They move along the star's rotation axis. And they reach the stalling shockwave. They collide with it. They push against it. The jets are not carrying much mass. They are narrow, but they are carrying tremendous energy. The jets are powered by the accretion disk around the newly formed neutron star or black hole. They are powered by gravity itself. The jets represent gravitational potential energy being converted into directed motion. And they arrive at the shockwave just when the shockwave is stalling. The jets revive the shockwave. They push against it. They accelerate it. They inject new energy into it. The stalling shockwave is restarted. The shockwave begins propagating outward again. It has new energy. It has new momentum. It begins tearing through the outer layers of the star. Boring outward, the jets bore through perpendicular to the shockwave. The jets move along the rotation axis. The jets break through the star's equatorial region first. They emerge. They escape into space. They create the characteristic bipolar jets of a hypernova. Meanwhile, the shockwave continues propagating outward from the core. It encounters less dense material. It accelerates. It gains speed. The material ahead of it is heated. The material is shocked. The material is torn to shreds. And then the shockwave reaches the star's photosphere, the outer layer where the star's radiation escapes into space. The shockwave breaks through, and the star becomes a hypernova. The explosion is unleashed. Stellar material begins streaming into space at velocities approaching light speed. The star is being annihilated. The star is becoming cosmic debris. The star is becoming part of the interstellar medium. And in that interstellar medium, something miraculous happens. Something that would change the chemistry of galaxies and seed the universe with elements necessary for life. But first, we must understand what powers the jets themselves. What keeps them alive? What fuels their incredible energy? The most powerful explosions in the universe are not hypernovae themselves. They are something that hypernovae create. Gamma-ray bursts, GRBs, the most luminous electromagnetic events ever recorded. More energy in a few seconds than our sun will emit in 10 billion years. Imagine that. A single burst lasting seconds, just seconds, releasing more power than an entire star's entire lifetime. The universe achieving luminosities that make every other object pale into insignificance. And hypernovae are the machines that create them. Hypernovae are the engines powering the most violent release of electromagnetic energy ever observed. When a hypernova detonates, when the jets escape into space, when the relativistic plasma reaches velocities approaching light speed, something becomes inevitable. A gamma-ray burst is born. Gamma rays are electromagnetic radiation, like visible light, like radio waves, like infrared and ultraviolet. But gamma rays are produced by the most violent processes. Gamma rays are created when energy is concentrated intensely. Gamma rays are the signature of extreme physics. A gamma ray burst is a cascade of gamma rays streaming outward at the speed of light. The burst is brief. Often, it lasts only seconds, sometimes minutes. The burst is intense. The flux, the number of photons arriving per unit area, can be staggering. During the brightest gamma-ray bursts, the photon flux can exceed that of the Sun by a factor of trillions. Trillions. A single gamma-ray burst can deliver more photons to Earth in 10 seconds than the Sun delivers in a year. The jets from a hypernova are the source. The jets are traveling at relativistic speeds. The jets are composed of plasma containing electrons, positrons, and photons. The jets are incredibly hot, billions of degrees. The jets are incredibly dense, matter compressed to extreme densities. As the jets move through space, they interact with the surrounding material. The jets collide with the star's outer layers that were blown off earlier in the explosion. The jets collide with circumstellar material, gas and dust that were shed by the progenitor star before its explosion. The collisions heat the material. The collisions accelerate electrons, and accelerating electrons radiate. They radiate at the frequency determined by their acceleration. They radiate gamma rays. The jets are also moving at relativistic speeds. This means that relativistic effects become critical. Time dilation is important. Length contraction is important. Lorentz beaming is crucial. Lorentz beaming is the phenomenon where radiation is preferentially beamed in the direction of motion when the source is traveling at relativistic speeds. Imagine a source producing radiation uniformly in all directions in its rest frame. Now accelerate that source to 99% of light speed. The radiation is no longer uniform. It is beamed forward. The radiation in the forward direction becomes concentrated. The radiation in the backward direction is suppressed. The effect is dramatic. The radiation intensity in the forward direction can be amplified by factors of thousands or millions. This amplification is Lorentz beaming. When a hypernova jet is traveling at 99% of light speed and pointing toward Earth, we observe the beamed radiation. We observe the amplified intensity. A gamma-ray burst appears far brighter than it would if it were traveling at lower speeds. The burst appears to be one of the most luminous events in the universe. But if the jet were pointing away from us, we would observe almost nothing. The radiation would be suppressed by Lorentz beaming. We would not observe the gamma-ray burst. This is why gamma-ray bursts appear so concentrated in their distribution across the sky. Bursts are only detected when the jets happen to be pointed toward Earth. Bursts are invisible when jets point away. The peak luminosity during a gamma-ray burst is incomprehensible. The brightest gamma-ray bursts reach luminosities of 10 to the 51st power watts, 1 duodecillion watts. Earth receives about 1.4 kilowatts per square meter from the Sun. During a gamma-ray burst, a detector on Earth can receive kilowatts per square meter from an object billions of light-years away. The inverse square law would suggest that a source at such tremendous distance should be invisible. It should be undetectable. But the source is so luminous that it overwhelms the inverse square law. The source is bright enough to be detected across distances that dwarf our galaxy. across distances encompassing billions of light years, across distances that reach nearly to the edge of the observable universe. And the burst is concentrated in time. The burst occurs in seconds, maybe 10 seconds, maybe 100 seconds. Some bursts are even shorter, a few tenths of a second. The intensity varies within the burst. There are spikes of brightness followed by fainter moments. The light curve, the plot of intensity versus time, shows complex structure, fine detail, variability on timescales of milliseconds. This variability reveals the internal structure of the jets. It reveals where shocks are occurring. It reveals where magnetic reconnection is happening. It reveals the turbulent nature of relativistic plasma, and it reveals that the entire burst is produced by a region that is surprisingly small, a region that might be only a few hundred kilometers across, a region the size of a small star producing the most luminous phenomenon in the universe. The gamma-ray burst can outshine an entire galaxy of hundreds of billions of stars, a single source brighter than billions of stars combined, a single event rivaling the output of an entire galactic structure. This is what a hypernova can achieve. This is the power that a magnetic jet can wield. This is the consequence of gravity crushing and magnetism focusing and rotation amplifying the explosion into a relativistic jet. The hypernova creates the engine. The engine powers the jets. The jets create the gamma-ray burst. And the gamma-ray burst becomes one of the few objects in the universe bright enough to serve as a cosmic landmark. Visible across billions of light years, detectable by satellites, observable by astronomers, catalogued and studied and analyzed. But gamma-ray bursts are only the electromagnetic signal. They are only the light. What about the matter? What about the material being ejected? What about the elements being created and scattered into space? The answer reveals why hypernovae matter to chemistry itself. Everything valuable on Earth came from a star, not our sun, not a supernova in our cosmic neighborhood, but from a hypernova, billions of years ago. In a galaxy far away, a star exploded. It tore itself apart. It scattered its ashes across space. And in those ashes was gold, silver, platinum, uranium, the precious metals that humanity treasures, the radioactive elements that power our technology, the rare elements that make our civilization possible, all born in a hypernova, all created in the intense heat and pressure of a cosmic explosion. This is not metaphor. This is not poetic license. This is literal fact. The gold in your wedding ring came from a hypernova. The uranium in nuclear reactors came from a hypernova. The thorium in old camera lenses came from a hypernova. You are wearing star stuff. You are using star stuff. You are touching the ancient remnants of stellar explosions. The periodic table of elements is a map of stellar nucleosynthesis. Hydrogen and helium were created in the Big Bang. Light elements up to lithium and beryllium were created in the early universe and in stellar interiors. Carbon, oxygen, and silicon were forged in massive stars. But the heavy elements, iron, nickel, cobalt, zinc, all the way up to uranium, these required something extreme. These required temperatures and pressures that only the most violent events could achieve. Supernovae create heavy elements, but hypernovae create them in abundance. Hypernovae create them in profusion. Hypernovae create them with an efficiency that supernovae cannot match. This is why hypernovae are the primary source of the universe's heavy elements. This is why understanding hypernovae is understanding where the periodic table comes from. nucleosynthesis in a hypernova occurs through processes called R process and alpha process synthesis. The R process is rapid neutron capture. In the intense neutron flux of a hypernova, atomic nuclei are bombarded by neutrons so rapidly that the nuclei cannot beta decay between neutron captures. Instead, nuclei accumulate neutrons. Iron captures a neutron and becomes cobalt. Cobalt captures another and becomes nickel. Nickel captures another and becomes copper. The nuclei climb up the periodic table, capturing neutrons at a rate faster than they can decay. The neutron flux is so intense that it drives nuclei far from stability. Nuclei are created that do not exist in nature under normal circumstances. Nuclei that are unstable. Nuclei that will eventually decay, but only after months or years. This rapid neutron capture process creates the heavy nuclei. Gold, silver, platinum, uranium, all the elements heavier than iron, all the rare and precious elements. The temperatures in a hypernova are high enough for another process as well. Alpha process synthesis. Helium nuclei, alpha particles, fuse together to create heavier nuclei. 3 alpha particles fuse to create carbon-12. This is the triple alpha reaction. A carbon nucleus captures another alpha particle to create oxygen shatters-16. Oxygen fuses with another alpha to create neon. Neon fuses to create magnesium. The process continues. Elements climb higher on the periodic table. The temperatures in a hypernova are sufficiently high that these reactions proceed rapidly, abundantly, efficiently. The star becomes a fusion furnace producing elements at a prodigious rate. The star is creating the building blocks of chemistry itself, but the abundance of heavy elements created in a hypernova is staggering. A typical supernova creates a certain mass of iron peak elements, a certain mass of nickel, a certain mass of cobalt. These masses are enormous by human standards, millions of tons, but by cosmic standards, they are modest. Hypernovae create 10 times more, 100 times more. Some hypernovae may create even more. A single hypernova event can produce more nickel-56 than a supernova, and nickel-56 is radioactive. It decays into cobalt-56, which decays into iron-56. These radioactive decays heat the ejected material. These radioactive decays power the brightness of the explosion. Hypernovae are powered by their own nucleosynthetic output. The explosion becomes brighter because of the elements being created. The iron peak elements, iron, nickel, cobalt, are created in the highest abundance. These are the elements that result from nuclear fusion reaching its limit. Iron cannot fuse into anything heavier without energy input. So iron becomes the most abundant heavy element. But beyond the iron peak, elements become progressively rarer. Gold is rarer than nickel. Platinum is rarer than gold. Uranium is one of the rarest elements, heavier than iron, that is created in significant quantities. The R process creates these rare heavy elements. The R process is the only mechanism in the universe that can create thorium and uranium in substantial quantities. Without R process nucleosynthesis in hypernovae and other extreme events, uranium would not exist. Life would not exist. Nuclear reactors would not exist. Uranium mining would not be a human endeavor. The entire technological landscape of civilization would be transformed. The ejector from a hypernova carries all these elements into space. The explosion scatters millions of tons of newly created heavy elements into the interstellar medium. The elements mix with the surrounding gas. They become part of the galactic clouds that will eventually collapse to form new stars, new planetary systems. Billions of years later, in a corner of a galaxy, far from where the original hypernova occurred, new stars form. Planets coalesce around those stars, and in the composition of those planets is the material from the hypernova, the gold in those planets, the uranium in those planets, the radioactive elements that will power geological processes, that will power chemistry, that will enable life. This is the cosmic legacy of hypernovae. Hypernovae are not merely violent explosions. They are forges. They are factories. They are the mechanism by which the universe enriches itself. The universe begins with only hydrogen and helium. Stars create carbon and oxygen and heavier elements. Massive stars create iron and silicon and elements up to the iron peak. But to create gold, to create platinum, to create uranium, you need a hypernova. You need an explosion so violent that it tears a star apart and creates heavy elements in the process. You need the combination of extreme temperatures, extreme pressures, intense magnetic fields, and relativistic jets that only a hypernova can provide. Every precious metal on Earth owes its existence to a hypernova. Every radioactive element in Earth's crust traces its origin to a hypernova. The copper in your wiring, the gold in electronics, the uranium in nuclear fuel, the thorium in old optical elements. All hypernovae, all cosmic catastrophes billions of years old, all violence that became chemistry, all destruction that became creation. And yet, the question remains unanswered. How do we know this is true? How do astronomers definitively prove that hypernovae created these elements? What observational evidence proves that hypernovae are the cosmic forges? The answer came only recently, in the 21st century. For most of human history, we saw nothing. The stars were dots of light, unchanging, eternal. Then, in 1987, astronomers observed supernova 1987A. A massive star exploded in the Large Magellanic Cloud. We detected it, we measured it, we studied it, and we realized that supernovae were not theoretical constructs. They were real, they happened. We could observe them. We could measure their brightness. We could analyze their light. But we still did not know about hypernovae. Hypernovae were hidden. Hypernovae were invisible. Hypernovae were beyond our instrument's capability to detect with certainty. We were blind to them, blinded by ignorance and lack of technology. For decades, we simply did not know what we were missing. Then came 1999, the year everything changed. Astronomers detected an explosion in a distant galaxy. They named it SN 1998BW. The designation seems ordinary, innocent, but the data was extraordinary. The brightness was wrong. The light curve was wrong. The spectrum was wrong. Everything about this event defied classification. The explosion was too bright, too energetic, too extreme. It did not fit the supernova category. It did not fit any existing classification system. Astronomers looked at each other. They whispered, was this something new? Could this be a hypernova? The theoretical models predicted hypernovae. The mathematics showed they should exist, but nobody had ever observed one before. Not with certainty, not with clear observational evidence. Now, they might have. The debate raged. Some astronomers argued SN 1998BW was an unusual supernova, a statistical outlier, a rare supernova at the extreme end of the distribution. Others argued it was something fundamentally different. A hypernova. The argument was settled by follow-up observations. Telescopes around the world observed the event. Satellites detected its radiation. Astronomers collected data. They analyzed spectra. They measured velocities. They calculated energies. And the evidence became overwhelming. SN 1998 BW was releasing 100 times more energy than a typical supernova. SN 1998 BW was ejecting material at 90% of light speed. SN 1998 BW was associated with a gamma-ray burst. SN 1998 BW was a hypernova, the first confirmed hypernova, the first direct observational evidence that hypernovae actually exist, the first proof that the theoretical models were correct. Science had advanced. Mystery had been solved, or so we thought. More hypernovae were discovered. GRB 030329, GRB 980425, GRB 130427A. Each event was more extreme than the last. Each event revealed new surprises. The events were associated with different types of stars. Some came from very massive stars. Some came from less massive progenitors. The explosion geometries varied. The jet structures varied. The energy outputs varied. But all these events shared common traits. All were connected to gamma-ray bursts. All ejected material at relativistic speeds. All were orders of magnitude more energetic than supernovae. The hypernovae were real. They were diverse. They were common. And they were reshaping our understanding of stellar death. Technology advanced. Telescopes became more sensitive. Detectors became more sophisticated. The Hubble Space Telescope observed hypernovae in unprecedented detail. The Chandra X-ray Observatory detected their high-energy radiation. The Spitzer Space Telescope measured their infrared emissions. The Swift satellite detected gamma-ray bursts in real time. Ground-based observatories followed up with detailed observations. Spectroscopy revealed the composition of the ejector. Polarimetry revealed the magnetic field structures. Photometry revealed the brightness evolution. Every new observation added pieces to the puzzle. Every measurement refined our understanding. Hypernovae became less mysterious. Hypernovae became increasingly well characterized. Hypernovae became ordinary. Or rather, hypernovae became an understood class of cosmic events with specific properties and predictable behaviors. Then came the James Webb Space Telescope, launched in 2021, beginning observations in 2022, revolutionizing astronomy. JWST can observe objects that Hubble cannot reach. JWST can detect faint sources. JWST can measure spectral details with unprecedented precision. And JWST has been turning toward the early universe, toward the cosmic dawn, toward the moment when the first stars were forming. And what JWST revealed was shocking. Hypernovae were common in the early universe, more common than supernovae. The early cosmos was populated with massive stars that lived fast and died violently. The cosmic environment was harsher, more extreme, more chaotic. JWST confirmed that hypernovae played a central role in seeding the early universe with heavy elements. Recent discoveries have uncovered exotic types of hypernovae. Magnetorotational hypernovae. These are hypernovae where the magnetic field and rotation are particularly extreme, where the magnetic to gravitational energy ratio is very high. These events are even more energetic than standard hypernovae. even more focused, even more capable of creating extreme conditions. Superluminous supernovae. These are events that reach absolute magnitudes exceeding -20, brighter than 100 million suns. Some of these may be powered by magnetorotation, a newly born magnetar spinning down and dumping its rotational energy into the explosion. Some may be driven by jets from a black hole. The full diversity of hypernova physics is still being discovered. The observational techniques continue improving. Gravitational wave detectors like LIGO have begun detecting the merger events that sometimes produce hypernovae-like explosions. Multi-messenger astronomy, combining gamma rays, X-rays, visible light, neutrinos, and gravitational waves, has given us unprecedented insights into the physical processes. High-resolution spectroscopy has revealed the detailed internal structure of hypernova jets. Polarimetry has mapped magnetic field configurations. Adaptive optics on ground-based telescopes has allowed astronomers to observe distant hypernovae with increasing clarity. We are not yet at the end of discovery. We are not yet at the point where hypernovae hold no mysteries. But we have crossed a threshold. We have moved from speculation to measurement, from theoretical prediction to observational confirmation, from wondering if hypernovae exist to understanding how they work. Every discovery raises new questions. Every observation reveals new complexity. Every measurement shows that the universe is even more violent than we realized. Hypernovae are not rare one-time events in a star's life. They are common occurrences throughout cosmic history. They are happening now. Somewhere in the observable universe, a hypernova is detonating. This very moment, today, tomorrow, in the next hour, in the next minute. These cosmic explosions are continuous. They are relentless. They are reshaping galaxies. They are enriching the cosmos with heavy elements. They are enabling the chemistry that makes planets possible. But what happens when a hypernova occurs near other stars? What happens when its radiation washes across nearby systems? What is the reach of a hypernova's destruction? A hypernova is not a localized event. It does not affect only the star's immediate surroundings. A hypernova is a cosmic-scale phenomenon. Its effects ripple across light years, across the galaxy, across intergalactic space. The radiation propagates at the speed of light. The material expands outward through the vacuum of space. The energy dissipates across the cosmos, and everything in its path experiences consequences. Everything in its path is transformed. A hypernova is not a localized explosion. It is a reshaping of reality. It is a force that restructures the cosmos on massive scales. The immediate vicinity of the hypernova is annihilated. Any planets orbiting the progenitor star, if they existed, are vaporized. The radiation pressure alone would be sufficient to strip away planetary atmospheres at distances of millions of kilometers. The stellar wind from the hypernova would sweep through the system like a cosmic hurricane. The intense heat would vaporize rock. The intense pressure would compress and shatter matter. Within a few light days of the hypernova, nothing could survive. No planets, no moons, no asteroids, no spaceships, no life. Everything would be obliterated. The region around the hypernova becomes a dead zone, a sphere of destruction, a volume of space where matter has been destroyed and atoms have been scattered. But the destruction extends far beyond the immediate vicinity. The gamma ray burst from a hypernova, if pointed toward us, would have devastating effects even at great distances. A gamma ray burst from across the galaxy could deliver enough radiation to Earth to damage ozone layers. radiation that would sterilize planetary surfaces, radiation that would kill organisms exposed to the sky. A hypernova in the Andromeda Galaxy, 2 million light-years away, would deliver enough gamma rays to cause biological damage on Earth. Thankfully, such an event is extraordinarily rare, but mathematically possible, physically plausible, a threat to be considered. The expanding debris from a hypernova creates a shockwave. This shockwave plows through the interstellar medium, the thin gas and dust between stars. The shockwave heats the gas. The shockwave accelerates it. The shockwave creates a blast wave similar to the blast wave from a nuclear explosion on Earth, but vastly scaled up. The blast wave can reach velocities of 30,000 kilometers per second initially. As it expands and decelerates, it still travels at thousands of kilometers per second centuries after the explosion. The blast wave can reach neighboring stellar systems. The blast wave can compress surrounding gas clouds. The blast wave can trigger the collapse of molecular clouds. New stars can be born from the compression created by a hypernova's blast wave. Destruction and creation intertwined. The enriched ejecta from a hypernova. The material containing the newly created heavy elements mixes with the surrounding interstellar medium. The material is distributed across light-years of space. The density of this material is low, far lower than any terrestrial substance, but the total mass is enormous. Millions or billions of tons of material enriched with gold, platinum, uranium, and other heavy elements. This enriched material becomes part of the galactic environment. It becomes available for incorporation into new molecular clouds. New stars form from these clouds. Those stars inherit the chemical composition. Planets forming around those new stars inherit the chemical composition. The heavy elements are now distributed throughout the galaxy. Within a hypernova's host galaxy, the effects are dramatic. The hypernova releases tremendous energy. The energy goes into heating the interstellar medium. The energy goes into ionizing gas. The energy creates expanding shells of hot gas that eventually cool and form spectacular nebulae. The hypernova changes the energy budget of the galaxy. The hypernova injects turbulence into the galactic gas. The hypernova can trigger star formation in nearby regions or suppress it by heating the gas too much. Galaxies containing multiple hypernovae over their lifetimes have very different characteristics than galaxies containing only supernovae. The chemical composition is different. The star formation rate is different. The structure is different. For galaxies near the hypernova's host galaxy, the effects can still be substantial. A nearby galaxy receiving radiation from a distant hypernova experiences increased ionization of its gas. The radiation can trigger changes in the chemistry of the intergalactic medium. The radiation can affect the rate at which gas cools in galactic halos. The radiation can influence whether or not new stars form. These effects are subtle, not dramatic, but they are real. They can affect the evolution of galaxies. The hypernova's neutrino output is equally remarkable. Neutrinos are nearly massless particles that pass through normal matter with barely any interaction. A hypernova releases an enormous flux of neutrinos. These neutrinos stream outward at nearly the speed of light. They carry away tremendous energy. They pass through everything, pass through planets, pass through stars, pass through us. The neutrinos from a distant hypernova could, in principle, be detected by neutrino observatories on Earth. The detection would tell us about the physical conditions in the hypernova core. The detection would provide information about the explosion mechanism that cannot be obtained from any other source. Neutrinos are messengers from the core. Neutrinos reveal the violence occurring at the hypernova's center. The distance over which a hypernova remains visible is extraordinary. The brightest hypernovae can be seen by Hubble Space Telescope across distances of billions of light years. At such distances, most objects are invisible. They are far too faint. Their light has been diluted by the inverse square law. But hypernovae are so luminous that they overcome the inverse square law. A hypernova can be detected across distances that encompass significant fractions of the observable universe's radius. This makes hypernovae cosmic beacons. This makes hypernovae cosmic lighthouses. This makes hypernovae useful for mapping cosmic distance scales and measuring the universe's expansion rate. A sufficiently nearby hypernova would be catastrophic for life on Earth. If a hypernova occurred within a few thousand light years, the radiation would strip our atmosphere. The radiation would sterilize the planet's surface. The radiation would kill all life. Mass extinction. Complete annihilation. But such events are extraordinarily rare. No hypernova has occurred close enough to affect Earth in the last billion years. None are known to be coming, but statistically, given enough time, such an event will eventually occur. Over timescales of billions of years, life on Earth faces existential threats from cosmic violence. The cosmic web itself is affected. Hypernovae inject energy and momentum into the intergalactic medium. Over cosmic timescales, with billions of hypernovae occurring throughout the universe's history, the cumulative effect is significant. The universe's large-scale structure, the filaments and voids of matter, has been shaped in part by the violent feedback from hypernovae. Without hypernovae and other violent events, the universe would look different. The distribution of galaxies would be different. The history of star formation would be different. Hypernovae are not mere local phenomena. They are architects of cosmic structure. This is the reach of a hypernova. This is the scale of impact. This is how a star's death reshapes the cosmos. And yet, all these violent, destructive processes create something beautiful, something necessary, something that enables life itself to exist. What cosmic truth lies at the heart of this paradox? We are made of stardust. Everyone has heard this phrase. It is treated as poetry, as metaphor, as beautiful symbolism. But it is literal truth. Every atom in your body heavier than helium was created inside a star. Every atom of carbon in your DNA. Every atom of oxygen in your blood. Every atom of iron in your cells. Every atom of calcium in your bones. Every atom of phosphorus in your neurons. All created inside stars. All forged in stellar furnaces. All born in cosmic violence. And the heavy atoms, the gold in your jewelry, the uranium powering reactors, the thorium in old devices, all born in hypernovae, all born in the most violent explosions the universe can create. You are not just made of stardust, you are made of hypernova dust. You are assembled from atoms that came from the death screams of the most extreme stars ever to exist. This changes everything. This transforms how we see ourselves. We are not separate from the cosmos. We are not observers standing outside the universe looking in. We are part of it. We are products of it. Our atoms are recycled cosmos. Our bodies are containers of ancient stellar material. Our consciousness is the universe becoming aware of itself. When you look up at the night sky and see the stars, you are seeing your own origin. You are seeing the furnaces that created your atoms. You are seeing the cosmic events that enabled your existence. The question, why do hypernovae matter, can be answered in one sentence. Without hypernovae, you would not exist. Not metaphorically, literally. The heavy elements necessary for your body's construction would not exist. The planets would not have formed. The chemistry would not have been possible. The timeline of life would have been different. You would not be sitting here reading these words. You would not be thinking about the cosmos. You would not be conscious. Hypernovae are not distant curiosities. Hypernovae are the foundation of your existence. But why does this matter? Why should you care about stellar explosions billions of light years away? Why should you invest emotional energy in understanding cosmic violence? The answer is profound. Understanding hypernovae is understanding the narrative of your own creation. Understanding hypernovae is understanding how you came to be. Understanding hypernovae is understanding the cosmic story that brought you into existence. Every discovery about hypernovae is a discovery about yourself. Every scientific insight into hypernova physics is an insight into the mechanism that created you. The journey from the Big Bang to human consciousness is a narrative of increasing complexity. The universe began as pure energy, pure simplicity, no structure, no elements, no chemistry. Then the first stars formed. These stars created the first heavy elements. Then successive generations of stars created even heavier elements. Billions of years ago, a hypernova occurred somewhere in our galaxy. The explosion scattered material containing iron and nickel and all the elements necessary for planets. That material became part of our solar system. It became part of Earth. It became part of the oceans. It became incorporated into the first molecules. It became incorporated into the first life. It became part of the evolutionary tree that eventually led to humanity. This is cosmic genealogy. This is the story of your ancestors. Not your human ancestors, your atomic ancestors. The atoms that make up your body have a lineage stretching back 13.8 billion years. They were created in stars. They were scattered in supernovae and hypernovae. They were incorporated into galaxies. They were assembled into new stars. They were incorporated into planets. They were assembled into molecules. They became part of life. They became part of you. You are not separate from this cosmic narrative. You are the latest chapter. You are the universe's expression of its own history. You are consciousness emerging from stardust. The violence that created you is profound. The stars that exploded to create your atoms did not do so gently. Hypernovae are catastrophic events. They are destruction on a cosmic scale. They are the deaths of stars. They are the annihilation of stellar structures. They are the creation of black holes and neutron stars and magnetars. They are events so extreme that they push physics to its limits. And yet, out of that violence came creation. Out of that destruction came the elements for life. Out of that catastrophe came the possibility of you. This is the paradox that lies at the heart of cosmic existence. Destruction and creation are intertwined. Violence enables beauty. Catastrophe enables existence. This changes how we should think about the universe. The cosmos is not a peaceful place. The cosmos is violent. The cosmos is extreme. The cosmos operates at intensities that dwarf human experience. But the cosmos is also the source of everything we value. The cosmos is the source of the elements we use. The cosmos is the source of the energy that powers life. The cosmos is the source of the atoms that comprise our bodies. We are not separate from this violence. We are the outcome of it. We are the universe's way of experiencing itself after billions of years of stellar explosions and galactic evolution. Understanding hypernovae is a form of cosmic archaeology. It is understanding the ancient events that shape the present. It is understanding the deep time that separates us from the hypernova that scattered the atoms that would become us. It is comprehending that our existence is contingent on events that occurred billions of years before Earth formed, that our consciousness depends on explosions that happened in galaxies that no longer exist, that our ability to observe and study the universe is enabled by the very processes we are studying. This is the catharsis. This is the profound realization. You are not an observer of the cosmos. You are an expression of it. The universe is not something external to you. The universe is you. When scientists study hypernovae, they are the universe studying itself. When you learn about stellar explosions, the cosmos is learning about its own violent history. When you contemplate your atomic ancestry, the universe is contemplating its own creation. We are the mechanism by which the cosmos achieves self-awareness. We are the tool by which the universe understands itself. We are consciousness emerging from 13.8 billion years of cosmic evolution. The hypernovae that created your atoms did not know they were creating you. They did not know they were setting the stage for life. They did not know they were enabling consciousness. They simply exploded according to the laws of physics. They scattered elements. They enriched galaxies. They contributed to the cosmic web. And in doing so, they made you possible. They made all of us possible. They made this moment where you are reading about hypernovae and contemplating your place in the cosmos, possible. So when you look up at the night sky, remember this. Remember that you are made of stardust. Remember that you are made of hypernova dust. Remember that you are an expression of the cosmos. Remember that the violence of stellar explosions created the atoms of your body. Remember that the light from distant stars is the light of your ancestors. Remember that consciousness itself is the universe becoming aware of its own history. We are the cosmos reflecting on itself. We are the universe asking questions about its own origin. We are stardust asking how it came to be. And in asking that question, we fulfill the cosmos's deepest purpose, to know itself, to understand itself, to contemplate its own beauty and violence and meaning. This is the revelation. This is the truth that hypernovae teach us. Not merely scientific fact, but existential meaning. We are not separate from the cosmos. We are its offspring. We are its consciousness. We are its voice. And when we study hypernovae, we are the universe studying the mechanism of its own creation. We are cosmic awareness achieved through human curiosity. We are the cosmos coming to understand itself through the intelligence it created. This is the cosmic truth. This is the revelation that should fill us with awe, with wonder, with profound gratitude for the violent, beautiful, catastrophic process that created us. We are children of hypernovae. We are stardust given consciousness. We are the universe knowing itself.